So why not I simply deliver a lecture on Zoom and record a whole video and use simply cut it into segments, and that is the same effect, right? So I'm going to upload this course, basically every course videos later after 12 o'clock, maybe in the afternoon. And so there will still be quizzes, okay? But since the quizzes come at a later time on Tuesday and Thursday, I will probably set a deadline in 3 days on Friday and Sunday. So that's what I'm thinking right now. So there will still be quizzes based on the lecture's contents, which will be released after the lecture. Okay. All right. And I have the participants window open. So if you raise your hand, I guess I can notice that. So during the lecture, if you have any question, raise up the little hand, the little blue hand. And if I don't recognize that, please just shout out in the channel, okay? All right, oops, let me just, turn to the first slide. So the topic today is going to cover the rest of the linear regression models. So far we have defined the task, right, using the example of predicting the housing prices using a bunch of features like the size, the year, the number of bedrooms, right? Okay. All right. So, and we also like basically formalize the question by defining the cost function. Okay, so the cost function is a metric that measures how good the model is. It basically measures the difference between the predicted value and the ground truth, the actual label value. Okay, and based on the goal of minimizing that cost, we come up with the first method, which is the normal equation method. And it is basically from the thought of finding the minimal points, right? By making the derivatives of the cost function with respect to all the parameters to be zero, and solving that, solving the resulting equations give us the solution to the parameters. So next, actually the focus of this actually for this whole course, when we talk about supervised machine learning models, especially neural network based models, we will the core of our method is about using the gradients, of the cost function with respect to the parameters. So the first in the first lecture here, we will introduce the gradient descent method. Okay, so basically it is a very iterative optimization algorithm. Okay, by iterative, I mean it is a step-by-step algorithm. And the goal of its goal is to find the minimum of a function, okay? And we start from the cost function for simple linear regression, which only has two parameters, theta 0 and theta 1. Theta 0 for the intercept and theta 1 for the slope, okay? So the general thoughts, okay, is we want to find the thetas that minimize the cost function, but we don't know where to start, okay? So we can simply start with some initial candidates, okay? And start from there and gradually approach the minimum, approach the target values. Okay, so the starting candidates values can be some random numbers because we have no idea where to start. Okay, so the term gradients may sound a new word to you, but it's actually you can think of it as a partial derivative. Okay, so it is defined on functions. Okay, and that function has a single target variable. Okay, so like the function here, y is a function capital F of x, so we can define the derivative of that function with respect to the predictor x here. Okay, so this is called, so this expression is called the derivative of the function. Okay, so whenever we talk about the derivatives, we need to specify which variable that derivative is respect to. Okay, so in this case, derivative is defined on single variable, but gradients, it can be defined on multiple variables, right? So in the case of simple linear regression, yeah, I see a good question. What is the motivation to use gradient descent? Well, I think I mentioned that, but it's good to mention that again here because in the normal equation solution, remember we need to compute the inverse of a very large matrix, which is x transpose times x. So if we have a lot of features in our data, so the x transpose would have a lot of rows and x would have a lot of columns. So to compute the inverse of a matrix that's so large is very computationally inefficient. So that's basically the reason why we need gradient descent. But gradient descent can do much more, way much more than solving a linear regression models. Linear regression models, it is solvable. We can obtain some analytical solution for linear regression problems. But for a lot of non-linear models like neural network models, logistic regression models. Well, logistic regression model is still kind of linear because it's just the outputs, it's different. But you know, for complex models, it's absolutely difficult to directly have an analytical solution like the way we have for the normal equation solutions. Okay, and yeah, let's carry on here. So gradients, it's kind of you can think of it as a derivative with respect to multiple variables. Okay, so if our variable here is a vector, so if x is vector, and it means there are multiple components in x. Say x, the vector x has n components or n dimensions, let's say. Okay, right? Basically the gradients of the function with respect to x is also a vector, right? With each component to be the partial derivative of the function with respect to that particular component here. Okay. All right, let's go to the next slide. Okay. So the purpose or the goal, or what we can do with using derivative is to measure how much the output changes if the input changes a little bit. That is actually based on the definition of a derivative of a function, right? So if we consider a simple linear function, I guess these are primitive mathematics knowledge here. The derivative of the function or of y with respect to x is computed by taking a small step along the x-axis, right? So when x changes from x1 to x2, the increment amount is x2 minus x1. And the derivative at that point is basically the ratio of the changes of y over the changes of x. And when that step is approaching a very small amount, okay? So that so the value of the derivative here, right, it basically measures how much y will change if x change for small amounts of value. Small amount of value, yes. And for like a nonlinear function here, we can do the same thing. We change the x, by a little value h in this case, and also the function will change by the value of here fx plus h minus fx. So that is a change of the y, right? So we basically extend this idea to the vector space. So if our inputs, inputs or the independent variable is say two-dimensional, okay? So if we define a function on two variables with x and y, then when we talk about the gradients of the function with respect to all the variables, we're basically talking about the derivative, the partial derivatives like this. And altogether, the gradients itself is also a vector, right? So in this case, the feature is like x, y, right? And the resulting derivative is the derivative with respect to x and the derivative with respect to y, which is also a vector of the same size. All right, so that's some basic concepts here. Okay, so let's dive deeper into the algorithm. Okay, so what gradients? Gradients have directions. Okay, and the direction of gradients, it's pointing to the direction of the fastest increase of function. Okay, let me quickly shut my window. It's some noise outside. Okay. Okay, and gradients points to the direction of the fastest change. Okay, so we need to utilize these facts. If we go opposite to the direction of the gradients point to, then we are actually going towards the direction that the function will decrease in the fastest speed. Okay, so because our goal is to find the minimum of some function, right? We try to find the minimum points of this cost function, and here the theta can be a vector. So the reasonable way is to go against the direction of the gradients, right? We want the cost function to decrease, so why not find the direction that the function will decrease in the fastest speed. Okay, so we can start with some randomly chosen values for the parameters, right? And we don't know if it is the minimum, and most probably it is not. Okay, so we need to choose a direction to change the initial value, to change that value, right? If we change the initial value for theta for a bit to theta 1, and that 1 is in the superscripts within parentheses, it means it is in our first iteration here. Okay, so so we want to change the parameters in a way so that the new cost function value will decrease a bit from the previous cost function's value. Okay, so the most efficient way is to choose a direction along which the cost function decreases fastest, okay, which is the opposite of the gradient points to, okay. And we need to repeat this step because we only move a very small step in each iteration, okay. We need to repeat the steps until some points. For example, we can repeat until the cost function doesn't change significantly. And we can consider that if the cost function no longer decreases, then that function already hits the minimum points. Okay. So let's use some example functions to show why this is the case. Basically we want to show why if we go against the direction of gradients, the function will decrease. I saw another question, will the cost function ever increase? Yes, it depends on which direction you go to. If you go along the same direction as the gradients, then the function increases, right? And we'll see in this example here. So let's use a quadratic function here. So this is a typical shape of a quadratic function, right? It's a facing up bowl shape. And if the coefficient a is greater than 1, so it's always facing up. So greater than 0, I mean. So remember the step of gradient descent, we need to first choose some random number, theta 0, right? And if we compute the gradients, we will find that the gradients is smaller than 0. It's a negative number because it is on the left side, right? It is on this side. So the gradient is decreasing. So the function y, the function j decreases with theta. That's why the gradients on this half is negative. And on the right half, the gradients should be positive, right? And right here at this minimum points, the gradients should be 0, right? And so we know the direction of the gradients. It is pointing towards left, because if you go along the direction that is red arrow points to, the function j will increase, okay? Since our goal is to minimize the cost function, so we need to go against this red arrow, right? We need to move towards the opposite direction of gradients by a small step, right? So how do we do that? How do we move towards the opposite direction? We can simply minus, right? We use theta 0 minus the gradients at point 0, at point theta 0. But we don't want to go with the step that's too big. We need to basically control how big a step is we want to go by multiply the gradients with some constants, alpha, okay? And we will call this alpha the learning rates, okay? So this is how big the step we want to go against the direction of gradients, okay? So let's say it again. So the negative here, the minus here makes sure that we are going against the direction of gradients, and the alpha determines how large our step is, okay? So that's how we update the values of theta. So we get a theta 1 from theta 0, okay? And because it's a step, little step, so we move theta 1 towards the right of theta 0 for a little bit, okay? So if alpha is smaller enough, so if alpha is not a big number, so the blue dashed lines will not go way to the right. It only moves towards the right for a little step. So the results will be that the theta 1 will be closer to the minimum points than theta 0. right? Because we only moved a little step, okay? And the cost function becomes smaller. That's the result we want to see, okay? And that's basically one iteration of the gradient descent process, okay? The whole thing is one iteration. So we want to repeat this step until a satisfactory theta n is reached. For example, if the theta n reaches this minimum point, then that's the point where we probably want to stop. So will it get stuck at the local minima? That's a good question. So whether a function have a local minima or a global minima totally depends on the nature of the function. A quadratic function has a global minima. We know that prior the process. We know that the cost function is a quadratic function, then we are very confident in using gradient method, because whenever we find a minimum, it will be a global minimum. Yeah, it's a convex function. But for the case of deep neural networks, and these are usually non-convex functions, and optimizing the cost function of a deep neural network-based models can sometimes result in that we don't reach the global minima, and we are not sure whether it's local or minimum. So these are very advanced questions that the technique of non-convex optimization technique deals with. Yeah. So far, right now all the techniques we have developed can pretty much make sure that even if it's a deep neural network, we can still achieve the minima points within a reasonable amount of time. Yeah. Okay, so that's the demo with 1D gradient descent. Okay, we can simply repeat the steps until we reach the minimum points. Okay, so if we take let's look at another case in this example. If we start with a different initial position of theta 0, then this time we're on the right and the gradients point to the right, right? So we need to move towards the opposites. That means we basically need to move towards the left side, right? That's where the black arrow pointed. So we will get a theta 1 out of theta 0, right? And theta 0, the cost function of j theta 1 is smaller than j theta 0. Okay, that's the one iteration done. And then we can repeat this step. So with this demo, we show that basically no matter where the initial point is, as long as we move towards the opposite direction of gradients, it's pretty sure that we can going towards the minimum point within this example of quadratic function. Okay, so let's go into the higher dimensional space. If the feature is a 2-dimensional vector with theta 0 and theta 1, right? That's basically the same thing we need to do. We can start with some initial values, theta 0, theta 1. That's the first iteration. We compute the gradients of with respect to the 2 parameters. Okay, so this time we take partial derivatives. Okay, when we so note that when we take the derivative of the function with respect to theta 0, then everything else are treated as constants, including theta 1. Okay, so when we compute the derivative with respect to theta 1, then theta 0 is also a constant. Okay, so say we have the direction of gradients pointed by indicated by the red arrows. Okay, and we move towards the opposites of the red arrow. Okay, which is a combination of the 2 vectors, right? And basically we need to go towards where the black arrows pointed to, and that will lead to the decrease of the cost function, and the red dot moved towards the bottom a little bit. And we basically repeat, we've got a new parameter values theta 01 and theta 11, okay? And in the next iteration, we basically do the same thing and moves the red dots towards the bottom more, okay? And we will repeat this step until we are satisfied, okay? Until basically this multivariate functions is basically minimized, okay? So if we summarize the gradient descent algorithm, we can start with, we basically start with some initial values of the parameters. And we need to repeat the steps until we are satisfied. And the step include, first, compute the gradients of the cost function at the current step with respect to all the parameters, okay? And we use it to update the parameter, okay, by minusing the gradients times some coefficients times some constants alpha, okay? And we repeat these two steps until we are satisfied and we obtain the final parameters. And the parameters, they are just the model we need. With these parameters, we can make predictions, okay? So